Greetings. We are going to look at finding the inverse for a 3 by 3 matrix. And to do that, we are going to use a theorem which tells us that we can take the reciprocal of the determinant of the inverse and multiply that by the adjoint of the matrix, and the product of those two things will give us the inverse for this matrix. I've already done a video about finding the determinant of a 3 by 3 matrix, so you can reference that if you need to. The next thing that we're going to do is we're going to need to find the adjoint of this matrix. And to begin that, we have to create a matrix of cofactors for this matrix. The cofactor is going to be -1 to the I plus j power times the submatrix and taking the determinant of that submatrix. How do we get the submatrix, and what is the I and j? The I and j are indexing what row and column you are in. So for instance, if you look at 1 here, it is in row 1, column 1. So that would be I and j would both be 1 in that situation. So we would have 1 plus 1 is 2. So we would have -1 to the second power. The submatrix that we're looking at is what we get when we eliminate the row and column indicated. In this case, it would be 4, 2, 0, 5. And we're going to take the determinant of this submatrix. So that is going to be a cofactor. We are going to create a new matrix of cofactors for every element in the original matrix. I'm going to call this new matrix C for now, and we are going to create this matrix. For the first entry, I am looking at element 1 here. Removing this row and this column, I have 4, 2, 0, 5 that I would like to have the determinant for. And this is going to be -1 to the second power because I'm at position 1, 1 here. Moving over to here, I'm still in row 1, but I am now in column 2, so this is 1, 2. So when I put my -1 here, this will be to the third power since 1 plus 2 is 3. And removing this row and this column, I end up with 5, 1, 2, 5. And we will continue to do that for every element in this matrix. Once we have all of this in here in our matrix of cofactors, we can go ahead and simplify this, and we will get back a 3 by 3 matrix of just individual numbers. All right, so this is our cofactor matrix that we have created based on the original matrix. And to get the adjoint that we need to take the transpose of this. The idea of the transpose is if you look at the main diagonal here and you kind of think of it as an axis, we're going to flip the numbers across this axis. So everything on the main diagonal here is going to remain where it is, but the -23 and the -10 will swap places. They will rotate around this axis. -8 and -4 will switch places as they rotate around this axis, and 13 and 2 will switch places as they rotate around this axis. So that is the idea of the transpose of this matrix. We designate this with a superscript T. All right, so hopefully if I've done this correctly, we have this as the transposed cofactor matrix, and this is what we are calling the adjoint of the original. So the adjoint of D is the transpose of the cofactor matrix created from D. We're going to take this matrix and multiply by the reciprocal of the determinant of D, and that will be the inverse of D. So this is going to act like a scalar multiplying over this, and this was our transpose of the cofactor matrix, and this is the reciprocal of the determinant of D. Again, this is going to give us a 3 by 3 matrix. We're going to have a lot of fractions now since everything in here is being multiplied by a fraction. And we also need to watch for sign changes. This determinant was a negative, so the reciprocal of the determinant is a negative. So we're going to see a lot of sign changes in here. All right, we have some things that are going to be reducible. So if you want to put it in reduced form, that will be your final answer. So with reducing the fractions, you have this form. If you would want decimals, that's available too. You could divide out all your fractions. Hopefully, if you have learned another way to do an inverse 3 by 3, this will be understandable and possibly more convenient than another method that you have been taught. This theorem that we have is pretty convenient. It's going to work for any square matrix. If you go back and try the 2 by 2, and instead of using the theorem that we've used in the past, try this theorem, it's still going to work out for you. Cheerful calculations.